All right, what is happening and which way is the heat going? So snow on the ground turns to liquid water. What kind of a process is that? Melting.
Oh my God, for a second I thought you said what kind of heat. Oh,
and then is it exothermic, endothermic, or is there not a transfer of heat in that process? Yeah, that's endothermic, because you have to put heat in to get the snow to melt, right? That's why it doesn't melt until it gets warmer. Water in a pan changes to steam. What's that called? Vaporization, yeah. And is that exothermic or endothermic? That's also endothermic. Once again, you need to put more heat into it to get it to happen. Another way to think about that is to think about this heating curve. Remember, everybody could probably draw something like that we've been looking at. And depending on which way you're going, you can think of things as being endo or exothermic. Energy is increasing this way. So if this is like 0, this is whatever. So if you're going from left to right, you're putting energy in. If you're going right to left, you're taking energy out. So that means that melting is going this way, which puts energy in, and boiling is going this way, which also puts energy in. All right, and then this one is probably the trickiest one. Calcium chloride dissolved in water. We did this in lab last week. What happened? You remember? It heated up. So is that a phase change? No, that's not a phase change. That's a chemical reaction. And then is it exothermic or endothermic? No, that one's exothermic. It got hot, remember? You dissolved it in water and heat was released. So heat went from the chemicals out to your hand so you could feel that it was hot. All right. So 1 point for each part of each of those. All right, on a hot sunny day, a metal chair heats up more quickly than a glass of water. What does this tell you about the relative specific heats? How can you explain that in terms of specific heat? Because you got the same heat input on a sunny day. The sun is shining on everything equally. So why would the chair get hotter than the water? Does a lot of things. Somebody take a turn. Who wants to go first?
Metal chair has less specific heat than water.
Yes, so the metal chair has a lower specific heat than the water. What does that mean?
It needs less heat energy to heat 1 gram of metal to
right.
1%, 1 degree.
Oops, so sorry, specific heat, that's correct. So specific heat is some energy unit like calories or joules per gram degrees C. So how much energy in calories or joules does it take to heat up a certain amount of a sample 1 degree C? If something has a lower specific heat, it means it takes less energy to heat it up. If it has a higher specific heat, it takes more energy to heat it up. So that means more energy per gram degree Celsius. So in this case, the metal has a lower specific heat. So with the same amount of heat, it goes up higher in temperature. The water has a higher specific heat. So the same amount of heat going in doesn't change the temperature as much. All right, then we got some ice cream. So this should have been kcals, but I'll just grade it however you did it. It's fine. So this is like what we did in the lab, where you had to measure you had to get the amounts off this food. So we got some delicious ice cream with 44 grams of carbohydrates, 28 grams of fat, and 8 grams of protein. So probably a fairly significant amount of ice cream, I would imagine, like a decent sized bowl. I'm really hungry right now, so this is terrible. But anyway, we have to multiply each of those by the energy density to get the total calories and then add it all up. Then the question asks for the answer in joules, so we have to convert it. Now, it doesn't matter what step you do when. You could actually convert all 3 of these into joules first and then do the multiplication and the addition. You could multiply first and then convert to joules and then add the joules together, or you could do everything and then convert to joules at the end. You should all get the same answer every time, every way. So I'm going to do everything first and then do the conversion at the end. So you'd go 44 grams of carbohydrates times 4 kcals per gram, and then 28 grams of fat times 9 kcals per gram, and then 8 grams of protein times 4 kcals per gram. Our calculator. That's 176. 28 times 9 is 252, and 8 times 4 is 32. All right, we add those all together, and we get, let's see, 284, that would be 460. Does that sound right? All right, so now if we're going to convert that to joules, it's 460 kcal, and then that's based on our conversion we're given up there. Oops, not 640. 460. 4184. 1.92 million. So if you just wrote that whole number, that's fine. That's the total in joules. And if you saw calories instead of kcals, you would get a different magnitude for your answer because the conversion would be a little bit different. But I'll grade it based on that, how you did it. All right, and then finally, the challenge one, the tough one. An ice bag containing this 275 grams of ice was used to treat sore muscles. Get an extra page here. When the bag was removed, the ice had melted, and the liquid water had a temperature of 24 degrees C. How many kcals of heat were absorbed? So this is heat going from your muscles into the ice. Once again, it can be helpful to think about what's happening in a graph. So first, the ice is melting. So if we imagine like this, we're going this way. So there's melting in this first part. And then cooling. Or sorry, I'm going the wrong way here. Again. So we're at 0. And let's say 24 is like here. So we're melting, and then we're heating up to 24. And those are two separate steps, so two separate calculations. First, the melting. It's 275 grams of ice times 80 calories per gram. Is 22,000 calories, or 22 kcal. And then the second part is the warming. So now the same amount of ice is going from 0 to 24 degrees C. And that's 275 grams of ice times 24 degrees C temperature difference times 1 calorie per gram degrees C specific heat. 600. Which is 6.6 kcals. So then the total is adding those two together, which is 28.6 kcals of energy. So you won't see a problem like this on the exam. Yeah, I'll give you a point for it. Yeah. Okay, so good quiz? No? All right, next one will be good. But the exam on Tuesday will be good, right? That's the important thing. Okay, let's move on. Oh, I lost all my notes here.
No.
Okay. So we were good with electron buckets. Okay. Good with naming and building ions? No, maybe? Questionable. Did you get these polyatomic ions down yet? Getting there? All right, let's test ourselves out a little bit first. And then with our last bit of time, we'll talk about some other things. Oh, first, let's check back at Blackboard. So if you look at the chapter objectives for this unit on ionic and molecular compounds, which is chapter 6, we didn't finish this chapter yet. So there's a whole bunch of stuff in these objectives that would not be on the exam next week because we haven't made it there yet. Basically, 13 on. Yeah. So 1 through 12 we've done. 13 through 23 we've not. Some of that we'll talk about today, but it still won't be on the exam on Tuesday. So you got to be able to get valence electrons, octet rule, ions, give the names, give polyatomic ions, all right, write formulas of metallic and nonmetallic things, write the formulas of the covalent compounds, that kind of stuff. So actually, sorry, we are doing 19 and 20 also because we already did that. That's just naming the covalent compounds, the easy ones where you use di and tri, that stuff.
What about number 8?
Yes,
So
that would be good. What is the Roman numeral in the ion refer to? The charge, right? When you write the name and you have that parentheses, yeah, that's what that is. Other questions about that? All right, let's try out some names. So I'm going to write down some formulas and some names, and I want you to give me the formulas for the names and the names for the formulas. Okay. What?
The names and formulas.
Whatever I give you, write the other one. Yeah. All right, so you got 5 of them here. Let's start with those. If you do need to look up a periodic table, please do so, because you will have that for the exam. But
We can print one out, like for the examination.
I'll have one for you. I'll have it printed out as part of the exam. All right, how'd these go? Maybe okay? All right, let's see how you did. NH4NO3, what are you gonna call that one? Yeah, good. Ammonium nitrate. So this one looks like a covalent compound because it's made up of nitrogen, oxygen, and hydrogen. The way that we know that it's ionic is because of how those things are kind of grouped. We know NH4 is a positively charged polyatomic ion, and we know NO3 is a negatively charged one. So the fact that it's split into those parts tells us this is not like nitrogen tetrahydride, nitrogen oxide, which coming up with a name like that might kind of signal to you that something weird is going on here anyway. So we have to think of those as the ions rather than the individual atoms. What about iron 3 sulfate? What would the formula of that look like? Fe2 sulfate 3, right? Yeah, let's look at how we build that one. So we look at the word iron sulfate and see sulfate is SO4 2 minus. Now there's, like I said, there's no way to kind of figure that out. We just have to know that sulfate is SO4 2 minus. Once we've got that, then we know the other ion has to be Fe3 plus, because that 3 in the parentheses tells us that it's a 3 plus iron. To finish finding the formula, we need to make sure these charges balance out. We've got to have as much plus as we have minus, because it's a neutral formula overall. So if the iron is 3 plus and the sulfate is 2 plus, the way to balance that is to have 2 of the 3 pluses and 3 of the 2 minuses. So you have 3 of the 2 minuses and 2 of the 3 pluses, and then the way we write that is Fe2 SO4 3 to show that there's those numbers, those proportions. All right, what about Na3P? Right, that one's going to be sodium phosphide, not phosphate, right? That's the next one. That's different. If it's just an atom by itself, it ends in ide, like phosphide, chloride, sulfide, oxide. Okay, so then calcium phosphate. Right, like that. So same deal. We have phosphate, which is PO4 3 minus, and calcium. The charge isn't given, but when we find it in the second column on the periodic table, group 2A, we know that that's charged. That one's charge is going to be Ca2 plus. So to make 2 plus and 3 minus balance out, it's just like making 3 plus and 2 minus balance out. You need 3 of the 2s and 2 of the 3s. And that comes out to Ca3PO4 2. What are you smiling about? Just enjoying this?
Oh, yeah.
Yeah. This is the best part of your day right here.
Just getting beat up right now.
Okay. Sorry.
No, I'm trying to learn. It's good.
You get it. All right. And then the last one. What did you get for this one? Yeah, good. The common mistake with this one is not realizing that it is actually a different kind of compound, one of these molecular compounds. And so something like that, somebody might say, well, it's sulfate because it's got S and O. That's not correct. Sulfate refers to a specific ion, SO4 2 minus. If it's just a neutral compound of sulfur and oxygen, that's a molecular compound, and that gets named as a molecular compound, sulfur trioxide. All right, so keep practicing these. We won't have a quiz on this stuff before the exam because the exam's on Tuesday, and it wouldn't really be helpful to have a quiz on Tuesday and then have an exam later on Tuesday. But go through the book homework and try to get as much practice as you can with these kinds of names, so you'll be ready for the exam. All right, should we move on? All right. So let's talk a little bit more about what it means for a compound to be a molecular compound. We kind of skipped over this before, and I just said, well, just molecules are from non-metals, don't worry about it. But now we want to worry about it, and we want to know what these things actually are and why they're different from the ionic compounds. The defining characteristic of a molecule is something called covalent bonds. Which is the sharing of valence electrons. Ionic compounds don't share electrons. You have positive ions, you have negative ions. They keep all their electrons, and they just kind of hang out around each other because negative and positive attract through those, we call that electrostatic forces. With molecules, the atoms are actually sharing their valence electrons. Remember the valence electrons, the ones, the outermost electrons? Those are actually being shared by molecules that would, or by atoms that would otherwise not have full valence shells. We talked about how atoms always want to have a full valence shell. One way to do that is from adding or subtracting electrons, and we call that ions. But the other way to do that is to share someone else's valence electrons and have them count with you. So let me give you an example. Hydrogen has how many valence electrons? Just one. It's just got one electron, so that's its valence. We can express that by putting a little dot here. It's called a Lewis dot structure. It's just the element with a little dot on it for the electron. How many electrons does hydrogen want to have in its valence shell to be totally full? Careful, yeah, it's 2, not 8, because that first bucket only holds 2, right? So it can't get 8. It could either have 1 or it could have none. And sometimes it has none. We call that a hydrogen ion. But another way that they can do this is to have 2 by sharing with another hydrogen atom. So another hydrogen atom also has 1 electron. These 2 atoms can get close enough that those electrons end up in both valences. So if those 2 atoms get close enough, we have something that looks kind of like this, where those 2 electrons count now for both atoms. So we would say the hydrogen on the left has 2 electrons, 2 valence electrons now, and the hydrogen on the right has 2 valence electrons. So in the molecule, they've now filled their valence shells. As long as they stay close to each other, they have enough electrons in their valence shells. If they were to separate again, they'd each have 1. But together in the molecule, we say that they each have 2 because they're shared. Does that sort of make sense so far? All right. These shared electrons are referred to as a covalent bond. And a covalent bond is simply that, just atoms being close enough together to share their electrons leads to a lower energy situation, and so they hang around each other. Another way that we write that, my colors here. Another way that we express a covalent bond is with a straight line. So you may have seen chemical structures with kind of like straight lines connecting atoms before. That's what those straight lines mean. We have to be really careful about that now. That straight line does not just mean atoms are close to each other. It specifically means that there are 2 shared electrons. So when we draw a line between 2 atoms, we're saying these 2 atoms are sharing 2 electrons. That also means that if we talk about a compound like sodium chloride, NaCl, that's not molecular, that's ionic. That's sodium ions and chloride ions. And so it is not okay to draw a line between sodium and chloride. And we should not have that line between there because those are not sharing electrons. Those are 2 ions with their own electrons that are simply charged and close to each other because of the charges. They're not actually sharing any electrons, so it's not appropriate to draw that line. So that line isn't just for any chemicals, any elements that are close to each other. That line is specifically talking about 2 shared electrons in a covalent bond. All right, so we got that. Let's look at larger molecules. Let's look at how this works with larger molecules. Let's draw a Lewis dot structure for fluorine, F. How many valence electrons does fluorine have? Now you can do all the buckets and stuff. What's the little shortcut for finding the number of valence electrons? If you look at the periodic table. The what? Yeah, it's 7. You look at the columns on top, And everything in column 1 has 1 valence electron. Everything in 2A has 2 valence electrons, and so on. It doesn't work for the middle ones. That's why they have Bs. But all the A's, it works. So F is in the 7A group, so that means 7 valence electrons. We draw those valence electrons around the atom, and we usually try to pair it up just for accounting purposes, but you don't have to. If I draw it like that, it's pretty obvious what's happening. There's one spot. There's kind of one spot missing. Because how many electrons does fluorine want in its valence shell? 8. So you can see if you draw 2, 2, 2, 1 that there's kind of an extra spot there, right? But what do you think fluorine does to fulfill that? We know one thing that it does is it makes an ion. What's another thing it can do based on this stuff? Yeah, it could make a covalent bond. It could share another it could share that one electron with something else and complete that. So let's first just look at another fluorine. That would be one way to do it. These 2 fluorine atoms could share those 2 electrons. Or another way we could write that is with that line for that bond, and we would actually keep all those other electrons around. Now, drawing a molecule like this, that is more than 2 or more atoms connected by covalent bonds, drawing it with using the lines and then the dots has a name. And this is called the Lewis structure. So later on, next week probably, we're going to get into how to actually draw those Lewis structures and how to draw structures for more complicated atoms or molecules as well. But this is basically how it works. It doesn't have to be the same type of atom. So fluorine, for instance, could join with hydrogen. And get that kind of a covalent bond, that kind of a molecule. Other atoms might need more than just that. So we can make build larger molecules using the same technique. Let's look at water. Now you probably know the formula or the structure of water. But we can show how this is built up based on the same kind of rules. Hydrogen has 1 valence electron, and there's 2 of those. And then oxygen, how many valence electrons does oxygen have? 6. 6. So that means that each of the hydrogens wants 1 more, and the oxygen wants 2 more. So they can connect together to do that. And these 2 can be shared, and those 2 can be shared. We can draw that in the dots and just do it like this. Or we can draw it in lines. Either way is an appropriate structure for water. All right. Now, where this gets a little bit tricky is you have to keep fulfilling this octet rule. When you make these compounds, these molecular compounds, you have to make sure that all of the atoms have full valence shells when you include all the shared electrons. So if we were building a structure like this and we didn't really know if this was right, the way we would check it is we'd look back at this oxygen and say, all right, how many electrons are around this oxygen now? Well, there's 2 here, 4, and then we count both electrons in this bond, that's 6, and then both electrons in this bond, that's 8. So we'd say, okay, oxygen has 8 electrons now in this compound. So it's stable, it's happy, that's probably right. All right. Let's try another one. O2, oxygen. This is oxygen gas. So we just said oxygen has 6 valence electrons. So we have something like that. If we share these 2 electrons with oxygen, we get that. So does that work? Does that follow the octet rule?
No,
No, why not?
because you're missing one, or they're missing one.
Yeah, they're still missing one. So the this oxygen has 2, 4, 5, 6, 7, and the other oxygen also has 7. So that's not okay. That tells us this is not the correct structure for O2. So what can we do? How can we fulfill that octet rule without adding any more electrons? Yeah, we can share more electrons. So instead of just sharing 2 electrons, what if we share another set of electrons? So we have now 2 sets of shared electrons. That means we can get rid of these and put another line for that second set of shared electrons. And let's count it out again. This oxygen now has 2, 4, 6, 8. And this one, 2, 4, 6, 8. So that works now. And this is what we would call a double bond. So each line we draw represents 2 shared electrons. So that double bond is 4 total shared electrons. Yes?
The highest amount like atoms share.
Generally 3. 3 pairs, so 6 total electrons. So a triple bond. Yeah. There has been reported a quadruple bond involving some metals, a couple unusual metals, but generally we just see 3. And the reason for that, you can think about from the octet rule, that if you shared more than 3, or certainly more than 4, you could have no other electrons around because now you're violating the octet rule. You have too many electrons. And that's only okay for some elements, some atoms. All right, so let's try another one where we're not dealing with the same kind of atom. And let's see what you can come up with. What's the name of this molecule? CO? Carbon.
Oxide.
Not quite. It's not. What?
Dioxide?
Not quite.
Monoxide.
Monoxide. 1 oxygen, right? It's a covalent compound, so it's not ionic. So it's carbon monoxide.
I have a question. So I didn't really understand. How can we tell, like, from the periodic table, that the number of electrons that the atom has?
The group numbers across the top.
Oh,
All the A's will have the number of valence electrons that the column number says. So 5A has 5 valence electrons.
so is hydrogen just the only one that doesn't want 8 electrons, or is that
Right.
just the only group?
That's the only one because it's only has the 1 bucket, doesn't have enough electrons. Hydrogen and helium.
Okay.
All right, so we've got CO. So let's first try to draw these dot structures for C and O. Figure out how many valence electrons each one has. And then see if you can come up with a structure where they share enough electrons to get 8 electrons for each. Let's see what you can do. No more and no fewer. You got it?
What's this? Each circle should be given 2 shared electrons. And that would end up with 1 more. But I think I'm gonna check.
Anybody run into trouble here? This one doesn't quite work.
Thanks.
Something weird happens here. We're almost out of time, so let me show you. The problem with CO, everybody got some nice Lewis structures of carbon and oxygen. And the problem is here that, all right, so you first share these and then these, and that's good. But if you try to write that down, then that gives this, which is fine for oxygen, but doesn't work for carbon. Doesn't have enough electrons, right? Carbon only has 6. But you can't share like these two more, because now what happens? That gets oxygen messed up. And actually carbon still doesn't have enough, because now carbon has 7 and oxygen has 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's really no way of getting this to work out that way. And this is a limitation with this model where you draw the Lewis dot structures, the little dots, and then you kind of make them come together like that. So there's a better way to do this. Let me show you the better way. In our last 5 minutes here, and we'll work more on this next week. Pool the electrons and redistribute them so that it works. The way that looks is like this. We take CO and we say, okay, carbon has 4 valence electrons and oxygen has 6 valence electrons. So that gives us 10 total valence electrons to work with. Now if we draw that, we say, okay, we want C and O to be connected. So that's 2 electrons we've used just there. And that means we've got 8 left to fill all the octets. So we've got 8 left. So that's 2, 4, 6, 8 for oxygen. And then 2 for carbon. Well, we still got a problem, right? Carbon doesn't have enough electrons. We've used all our 10. But now, because we've pooled them, we can distribute these anywhere we want. So we can say, well, instead of these 2 just stuck on oxygen, why don't we put them down here shared? And instead of these 2 stuck on oxygen, let's put them shared. Now, we've got 3 pairs of shared electrons, 2 pairs of unshared electrons. We still have 10 electrons accounted for here. So 2, 4, 6, 8, 10. And each atom has, let's see, oxygen has 2, 4, 6, 8, and carbon has 2, 4, 6, 8. So that actually works. But we had to actually, so that tells us something about what's happening in molecules, that it's not just that each one comes with its own electrons and they're shared evenly, but sometimes one of the atoms virtually has to give its electrons to the other atom to get stuff to work out properly. So sometimes it's not just this kind of even sharing, but it's kind of more of a redistribution of the electrons. All right. So we'll see some examples of that and how that works in next week, but that's good for now. So please have some good studying, practice those names and other stuff that we've been talking about, electron counting. And I will see you on Tuesday. So Tuesday we'll meet in here first. I'll answer questions if you got them. We can talk about whatever. Sometimes people just like to have kind of an open study time for last minute stuff where I'm just here to answer things that come up. So however you want to use that time, and then we'll go upstairs and do the exam.